So you may recall last Friday, we were taking a look at L'Hopital's rule, and we saw that that actually allowed us to find a limit where the limit originally would come out to saying 0 divided by 0. And so that gave us a way that at least when dealing with limits, we could figure out what 0 over 0 equaled. Remember, it equaled different things depending on the original equations that gave it to us. Today, we're going to be going a couple different places with it. We're going to start with this, though. Infinity divided by infinity. Now, it's not just 1, or at least not always. It can be 1. It can vary. In fact, it varies just as much as the 0 divided by 0 varies. Remember the notes that we took down on Friday on L'Hopital's rule? I had you leave a little gap there. That gap now gets filled in with this part right here. That we can also use it if it gives us infinity over infinity. So here's a problem that we're going to use to practice this idea. We're going to be finding the limit as x approaches infinity of this rational expression. Now remember, with L'Hopital's rule, we still always start by trying to find the limit using one of our other methods. And so, like, looking back, remember direct substitution is always where we start when we're trying to find the limit. Well, notice if I plug the infinity in for x there, I end up with infinity over infinity. That's that indeterminate form that's new today. Okay? Can we factor this?
Yeah. No.
Doesn't look like it to me. It certainly will not factor and reduce anyway. Multiply by the conjugate, nope, that wouldn't be relevant here. Combining fractions, nope, that wouldn't be relevant here. So I'm going to go ahead and tell you right here then that we're going to go ahead and use L'Hopital's rule. Now remember, when doing L'Hopital's rule, that means we got to find the derivative of the top and the bottom. Not the derivative of the fraction, but the derivative of the top and the bottom individually, right? So let's go ahead and do that here.
Okay.
So we're going to get the limit as x approaches infinity of, what's the derivative of 2x plus 7?
6x.
2. What's the derivative of 3x squared minus 5?
6x.
All right, now let's try plugging in the infinity and see what that gives us. So then the 2, of course, on the top stays at 2. On the bottom, we're going to be doing 6 times infinity.
Oh, so it's 2 infinity.
Infinity is a weird thing. It's more of a concept than a number. 6 times infinity is infinity. Some of the rules are a little bit different, as we're going to look at in more depth here in a moment.
It's 6.
So if you take 2 and you divide it by infinity, that's 2. Well, think about, like, as it's approaching this, you know. As you take 2 and divide it by bigger and bigger numbers, you're getting a smaller and smaller number, right? Something closer and closer to 0. So 2 divided by infinity is 0. And so our answer here for this problem is that my limit equals 0. But that being said, you actually could have answered this question earlier this year too.
Yeah,
Oh yeah, because we know. I just guessed.
This is bottom heavy.
Infinity or negative infinity.
Remember, we saw when dealing with rational expressions, bottom heavy ones always have their asymptote at 0, and so it's approaching 0. Well, this just proved why that works.
What?
We just used L'Hopital's rule to prove why anytime it is bottom heavy, you will end up with infinity on the bottom and some number on top. And anytime you do a number divided by infinity, you get 0. Now, in that problem, we saw this fact in use. That if you take any number and divide it by infinity, it's going to give you 0. But there's a few others that come up along the way too. If you have infinity divided by any number, doesn't matter how big that number is, infinity divided by anything is just still going to be infinity. But then, I know sometimes people then say, but what about infinity over infinity? Remember, that's our indeterminate form. That's the one that we're working with today, and that we have to use L'Hopital's rule in order to actually be able to figure out. Only relevant when we're talking about limits here. So, like if we take a look at this one as another example of it, if I'm going to be using L'Hopital's rule here, which technically we would have to use there, I'd find derivative of the top, derivative of the bottom, and then I'd have the limit at first of 24x over, 8x.
But you didn't plug it in. -1.
And then, -1, thank you. And then we'd do the derivative of top and bottom of that because we're still getting infinity over infinity. And so then I'd have 24 over 8, and 24 over 8 equals 3. This limit does equal 3 here. Now, this is another example, though, about one that we could have come up with before. Way back when we were first doing these, we saw that when it was balanced, you would do the coefficients divided, the 12 divided by 4. And so, again, we just use L'Hopital's rule to verify why does that work. Now, if you're given this kind of problem and you're asked to find that limit, do you have to use L'Hopital's rule? No, we've talked about it before, but I want you to see why it works, right? Because let's bring it back and relate it back to it. And so taking a look at how this one would work, based on our previous work, we saw that when it was top heavy, it was approaching infinity or negative infinity. Here we can see why that is, because if we use L'Hopital's rule here and find the derivative of the top, derivative of the bottom, we end up with like 15x squared over 18x minus 7, then derivative top and bottom again, because we still have infinity over infinity. And so then that would give me 30x over 18. Now, if I plugged in infinity, we'd have infinity over 18, which we just saw
Infinity
equals infinity. And so that's why when it was top heavy, it would actually give us infinity or negative infinity, depending on the signs involved, as our answer. And so just kind of bringing it back to some of that old stuff. But, of course, L'Hopital's rule is not just useful for rational expressions, just the polynomial over the polynomial, right? Now let's see how we deal with one where we can't just say it's top heavy, bottom heavy, or balanced, or whatever. And so when we approach one of these, we of course start the same old way. So we start by trying direct substitution. That even tells us if we can use L'Hopital here. If I plug in infinity, the natural log of infinity, it is infinity. And infinity minus 1 is infinity. So yes, this does start out as infinity over infinity. So it's an indeterminate quotient here. Is there a way that I can factor and reduce it? No. Conjugate? No. Combined fractions? There are no fractions within our fractions, so no. So yes, this is a situation where we have to use L'Hopital. In order to do that, we're going to go ahead and find our derivative of our top and bottom individually. So, limit as x is approaching infinity. What is the derivative of natural log?
1 over x.
What is the derivative of x minus 1?
1.
Now let's simplify that a little bit here. And so that would then just be the limit as x is approaching infinity of 1 over x divided by 1. That's just 1 over x. All right, now let's try plugging in infinity, see what that gives us. If we now plug in infinity, I have 1 over infinity.
0.
Anything divided by infinity, yes, is 0. And so that's our answer. And so in this case, when I find the derivative of top and bottom originally, I still end up with an infinity over infinity situation. And so I take the derivative again. But in this case, now I end up with infinity over 2. Infinity over 2 then equals infinity. So we know this one is then approaching infinity as x approaches infinity. So our y values are approaching infinity. So that tells us, like if we're just looking at the graph of this, that I know that in my graph, this thing is going to be heading up and to the right as we're heading as far out as we can go. Now, another type that we're going to be taking a look at today is indeterminate products. So far, we've only seen indeterminate quotients. Now, indeterminate products can happen as well, because if you look at this example, 0 times anything we would say is 0. but anything times infinity is infinity.
No, but infinity is a
Which
number.
one wins?
It would be 0, because infinity would be a
Th-
number.
This one's another one of those indeterminate type of things.
Wouldn't it be 0?
It's going to vary. So as we take a look at this, when it's given in the context of one of these limit problems, we actually can find solutions. And just like our indeterminate quotients, it's going to vary depending on what the equations are that are involved in the limit problem. So to illustrate that, we're going to take a look at this one. So go ahead and write down this example problem, then we're going to work it through together. All right, so with this one, of course, we always start by just trying the direct substitution. The square root of 0 is 0, times the natural log of 0. The natural log of 0 is what? Now, some of you are having a tough time remembering what natural log of x would be at 0. Well, if I graphed natural log of x, remember it's one of those. We got an asymptote at 0, which is why we're looking at the limit as x is approaching infinite, or x approaching 0 from the right.
Wait, so would that mean?
And so notice it's heading straight down, so it's approaching negative infinity, yes. And so this is saying 0 times negative infinity. That's an indeterminate form. And so we're going to be using L'Hopital's rule again. But remember, L'Hopital's rule says that I can take the derivative of the top of the fraction and the derivative of the bottom of the fraction. We don't have a fraction here. And so step 1 is that we have to make it a fraction. So we are going to rewrite our product here as a quotient. So I'm going to take these two parts and I'm going to put one of them in the bottom of a fraction. Now, in order to do that, we do have a question there though. Which one do we want to put in the bottom of the fraction? I have two options. I could rewrite it by putting the square root in the bottom like this, or I could put the natural log in the bottom like that. Well, if I look ahead a little bit, I'd have to be taking the derivative of top and bottom. Notice that if we do that, they both are kind of ugly. We got to deal with that, yeah. But you'll notice the second one over here, we still have natural log in there, which is still going to be negative infinity, which is going to be kind of a pain for us. So we don't want to have to deal with that one. We want to instead go with the left side. So we're not going to use this one. A general rule, if you are going to end up with natural log of x to the power of negative 1, it's probably not going to be the best way to do it. So we're going to go ahead and use the one on the left here. Now, when I found that derivative of the top and bottom, of course the derivative of the top is fairly straightforward. Natural log of x is 1 over x. But the derivative of x to the negative 1/2, make sure you understand why we got that there, because sometimes we get a little tripped up, especially when it's sitting in a fraction already. Remember, pull the original exponent out front, hence the negative 1/2. Then we're subtracting 1 from the original exponent to get the negative 3/2. It's very tempting to turn that into a positive 1/2. All right, now once we have that derivative, I need to clean it up. I need to simplify this. And so, you notice over here I've created a fraction. I'm going to just start building my fraction in. So, the 1 over x that's on the top, I'm going to put the 1 into the top and the x into the bottom of my new fraction. Next thing, we're dividing by negative 1/2. Dividing by negative 1/2 is the same as...
Timesing by negative 2.
Yep, multiplying by negative 2. And so then that means that on the top, I'm going to multiply that by negative 2. So I'll go ahead and just turn that 1 into a negative 2 there. And then we got x to the negative 3/2. Remember this negative exponent here flips it in the fraction. And so then I'm going to have x to the positive 3/2 in the top. Okay, I now used everything in here. All right, now notice this can still simplify though, right? Notice the x's are going to reduce. So let's go ahead and reduce those down. We end up with the limit as x is approaching 0 from the right of, well, still got the negative 2 there. And then we're going to do 3 halves minus 1 on the bottom. So that's going to be x to the 1/2, or in other words, just square root of x on the top. The only thing left on the bottom is just the 1, so it's just negative 2 root x. That is now a lot simpler, right?
What happened? Can you explain?
And so at this point, now that we have a much simpler equation, we try substituting again. If I plug in 0 for x, negative 2 times 0 is? 0. And there we got our final answer. It's 0. Now, when doing this particular problem, we do have to take our cotangent times sine here and turn it into a fraction. We got to turn it into a quotient. You got a couple different options actually about how you can do it. The way my mind works, for whatever reason, whenever I see the cotangent, I tend to think of it as cosine of 2x over sine of 2x. And then the sine of 6x is still there. And so when I do this, this is the way I naturally tend to go. That being said, I'm not going to do it that way this time. I'm going to force myself to break out of that a little bit, because there is another way, and I want you to be aware that there's another way that for some of you might seem a little bit easier. But again, either way can work. So what we're going to do here is we're going to do the limit. I'm going to keep my notation as x approaches 0. I'm going to write sine of 6x on the top. And I'm going to put my cotangent into the bottom. But I don't want to write it as 1 over cotangent. Because what does 1 over cotangent equal? Tangent. So I could actually just write it as tangent of 2x in the bottom. So you notice there's 2 different ways to do it. The way that I tend to do it, the way that I mentioned first, it will work, although you have to use product rule when you do the top. For some of you, this is going to seem much simpler, and that's fine. But let's go ahead and work from this form, just so we're all working from the same form. Go ahead and please now find your derivative of the top and find your derivative of the bottom. So now that we've gotten our derivatives, we can go ahead and start looking to see, can I now substitute in? Now, I actually skimmed over because I had already done it in my head, so I didn't think to say it. But at the start there, we had to use L'Hopital's rule because when we plugged in the 0, we ended up with infinity times 0. So that's why we had to do this one, remember. All right, so now I'm plugging in my 0 for x in my new equation here. What is the cosine of 0? 1. So that means the top is going to be just 6 times 1, which of course is just 6. And on the bottom, we're going to be doing secant of 0. Secant, remember, is 1 over cosine. We just saw cosine of 0 is 1. 1 over 1, of course, is 1. So secant squared of 0 just equals 1.
That's 3.
And so it's 6 over 2. And 6 over 2 equals 3. And so our limit is approaching 3 here. We started, remember, with taking a look at using L'Hopital's rule for doing an indeterminate quotient, where we ended up with 0 divided by 0, or infinity divided by infinity. Notice that with these, where we have the indeterminate product, in order to do it, I basically turned it into the quotient. In order to use L'Hopital's rule like this, we're just always taking the original and reformatting it into a quotient like this. So force the division into it, and then you can go ahead and do it.